Evaluate integral 0 to 1 plus I, z, dz along line y equals x, parabola y equals x square, and state whether the line integral is independent on the path or not. Starting the solution, where the limits are given in complex form, and we write them in coordinate form, where x is abscissa and y is ordinate. We get points 0, 0 and point 1, 1. We know that z is a complex number x plus iy. Differentiating z, we get dz equals dx plus I dy. Putting the values in the integral, we get integral 0, 0 to 1, 1 x plus iy into dx plus I dy. Diagram is not compulsory to draw in exam. Here it is drawn to make you understand better. Let's consider the first line equation, which is y equals x. Here, the line given is from 0, 0 to 1, 1. In our first step, we have our given equation y equals x. Then we differentiate the given equation. Thus, we get dy equals dx. In the third step, we convert f of z and dz in single variable. In this equation we can convert it in x or y. Any one of them can be preferred. Here, we convert y as a function of x. Thus, from 1 and 3, we get f of z equals x plus ix. And from 2 and 3, we have dz equals dx plus I dx. In fourth step, we substitute the converted values in I. In the last step, we consider the limits of the same variable. Here it is x, so we take the x limits 0 to 1, and then integrate further. We take x and dx common from the equation, and then take the constants outside to simplify the equation. After integrating, we get I1 equals 1 plus I square, x square upon 2, where limits of x is 0 to 1. Simplifying the definite integral, we get I1 equals 1 plus I square, 1 square upon 2, minus 0 square upon 2. Simplifying further using a plus b the whole square, we get I1 equals 1 plus 2y minus 1, into 1 upon 2. Canceling out 1 and 2, we get value of first line equation as I. Now, considering the second line equation, which is y equals x square, which is a parabola. Here, the parabola given is from 0, 0 to 1, 1. In our first step, we have our given equation y equals x square. Then we differentiate the given equation. Thus, we get dy equals 2x dx. In the third step, we convert f of z and dz in single variable. In this equation we convert y as a function of x, as it will be easier to simplify, otherwise we'll get the equation in fractions. Thus, from 1 and 4, we get f of z equals x plus ix square, and from 2 and 4, we get dz equals dx plus 2ix dx. In the fourth step, we substitute the converted values in I. In the last step, we consider the limits of the same variable. Here it is x, so we take the x limits 0 to 1, and then integrate further. We take dx common from the equation, and then multiplying the terms, we get I2 equals integral 0 to 1, x plus ix square, plus 2ix square minus 2x cubed, into dx. After simplifying the equation, we have I2 equals integral 0 to 1, x plus 3ix squared minus 2x cubed into dx. After integrating, we get I2 equals x squared upon 2 plus 3ix cubed upon 3 minus 2x raised to 4 upon 4, where limits of x is 0 to 1. Solving the definite integral, we get I2 equals 1 squared upon 2 plus 3i into 1 cubed upon 3 minus 2 into 1 raised to 4 upon 4 minus 0 squared upon 2 plus 3i into 0 cubed upon 3 minus 2 into 0 raised to 4 upon 4. Simplifying further, we get I2 equals 1 upon 2 plus I minus 1 upon 2 plus 0. Thus, after cancelling out the terms, we get the value of second line equation as I. We have to see whether is our line integral independent on the path or not. For that we compare the two line integrals. So here, from a and b we have I1 equals I, and I2 also equals to I. Here, we see that I1 equals I2. Thus, as we get same values for both the equations, we say that line integral is independent on the path.